Greetings, class, and welcome to part 2 of our second unit. In this particular section, we'll be talking about some of the different types of chemical bonds. Now, before we talk about chemical bonds, we do have to review from the previous lesson when we talked about electrons. We talked about electrons located in their different energy levels or electron shells. We mentioned that the most important of these electrons were the electrons in the outer shell. And those electrons in the outer shell, remember, are called valence electrons. And these are the electrons that are going to be involved in the formation of chemical bonds. In some cases, the electrons will be shared. In other cases, they'll be gained or lost, depending on the type of bond that forms. And of course, here is our periodic table where we can see all of our elements. We can see the groups, the periods, and if you remember from the previous lesson, the groups will tell us the number of valence electrons. For example, the elements in group 1 will have 1 valence electron, group 2 have 2 valence electrons, and so on and so forth. And then going horizontally, the periods will tell us the number of energy levels that we find for each particular atom or element. Here's an atom of carbon. If we look at carbon here, we can see carbon has an atomic number of 6. So it has 6 protons, has an atomic mass number of 12, so it has 6 neutrons. And it also has 6 electrons, 2 in the first energy level, and then 4 electrons in the outer shell. It's these electrons in the outer energy level, the valence electrons, that will be the ones that will be involved in forming different types of bonds. Since carbon has 4 valence electrons, and this shell here can hold up to 8, it has the ability to form 4 additional bonds. And then if you look at some of the other elements here, we can see some of these dot diagrams. Here we can see the amount of valence electrons. Elements in group 1 all have 1 valence electron, regardless of the size of the atom. You can see sodium has many more electrons than, say, lithium, but they still have the same number of valence electrons. It's also the same for group 2. You can see these elements have 2 valence electrons. Group 13 on the other side of the periodic table, you can see have 3 valence electrons. Now, the first type of bond that we're going to talk about is a covalent bond. In a covalent bond, the atoms attach to each other by sharing their electrons. So each one of these atoms is joining together, and what they're trying to do is they're trying to fill their outer shells. So they're trying to create this complete outer shell, and to do that, they'll share each other's electrons to create that. And in the case of covalent compounds involve a nonmetal joining together with another nonmetal. So we're talking about elements on the right-hand side of the periodic table. In the case of covalent bonds, there's 2 different types. There are nonpolar covalent bonds. In this case, the electrons are shared equally between all the elements involved in the compound. And then you have polar covalent bonds. In this case, you have the electrons, there's kind of a buildup of electrons in one particular spot in the molecule. And therefore, you get what's called this kind of electronegative area. And that area has more electrons than the other part of the molecule, therefore creating what are called poles. And you get this kind of polarity effect where you have a slight negative charge and a slight positive charge. So you can see in this example here, this is an example of a covalent bond between 2 hydrogen atoms. We call this a diatomic molecule because it's a molecule involving 2 elements that are the same, hydrogen, hydrogen. You might have oxygen, oxygen, O2. That's another example of a diatomic molecule. And we use the word molecule when we're talking about covalent compounds. And here's some other examples of covalent compounds. Let's hone in on the oxygen here for a second. You can see another example of a diatomic molecule. See how they share the electrons here? By sharing them, it creates a full outer shell for the 2 atoms. Same with the hydrogen here. In the case of methane, We have carbon, which we said before had 4 spaces left. Since it has 4 valence electrons, it has 4 spaces left to create that full outer shell, so it can actually accommodate 4 hydrogens. That's how we end up with CH4. And in the case of water, H2O, we add a couple of hydrogens here to add those extra valence electrons to fill up oxygen's outer shell. But notice in the case of water, look at how all these electrons are kind of concentrated here. And there's very little electrons on this side or this side here. This is an example of a polar covalent compound. And since it has such a buildup of electrons on one side, it has a slightly negative charge here, whereas the hydrogens end up with a slight positive charge. This is an example of a polar molecule, since it has poles to it. In the formation of an ionic bond, you have what are called ions, and an ion is an atom with an electrical charge. So you have ions of oppositely charged particles attaching to each other. And what happens in an ionic bond is you have one element giving electrons and the other element taking electrons. And generally an ionic bond occurs between a metal and a nonmetal. When you have ions joined together, giving and taking electrons, we end up with an ionic bond, and it's that transfer of the electrons, they're not sharing, they're transferring, that creates the attraction. And another word we use sometimes to describe an ionic compound is a salt. A salt is a metal and a nonmetal together, and quite frequently, the nonmetal will come from group 17, which are the halogens, whose name literally means forms salt. And a lot of times these particular elements will join together with elements in group 1 because the halogens have 7 valence electrons and the alkali metals have 1 valence electron, so they fit together quite nicely. And here's a great example. Sodium has 1 valence electron. Chlorine has 1 space. So in a chemical reaction, these guys will join together and you'll end up with sodium chloride. Notice sodium loses its electron, so now it has a full outer shell. Chlorine gains it, and it has a full outer shell. But notice what happens. We have 2 ions that form. Sodium becomes a positive ion, and it has a charge of positive 1 because it gave away 1 electron. So now it has 1 more proton than electrons. Chlorine gains an electron, so it takes on a negative 1 charge because it gained 1. Metals are electron donors, and they become positive when they form ions. Nonmetals are electron takers, and they become negative when an ionic bond occurs. Here's an example of salt right here, sodium chloride. Look at the intricate lattice work that's created between the alternating sodium and chlorines, giving it that crystalline shape and structure. Another type of bond that we're going to talk about is called the hydrogen bond. And the hydrogen bond is a little bit of a weaker bond. It's not like as strong as, say, an ionic bond or covalent bond. It's almost, imagine like between the molecules, say, for example, of water, the bond is more like, imagine one of the molecules has this incessant desire to shake hands. So it's quickly grabbing a hand, then let go of it, shaking another hand, letting go of it, grabbing another hand, so on and so forth. So the bond is not as structured, as permanent as like an ionic bond or a covalent bond, but it is another type of bond. And it is this particular type of bond that gives water its very unique properties. The hydrogen bond occurs when you have, for example, a water molecule. You have the polar sides. Remember, since it's a polar molecule, you have the oppositely charged polar sides become attracted to each other. Water has that, that V shape where it has the negative side from the oxygens and the positive sides from the hydrogens. Okay, remember, the water molecule itself is a polar covalent compound, which, like I said, makes it polar. But since it does make it polar, now you could have one water molecule attracted to another. So the oppositely charged sides of each individual water molecule are now slightly attracted to each other. So one water molecule will attach to another molecule, to attach to another molecule, and what holds the water molecules together is the hydrogen bonds. So you have the individual covalent bond that holds the individual water molecule together, but then you have the hydrogen bonds that hold the water molecules together. And again, here's the polar covalent compound that is the water molecule. Okay, so this is the covalent bond that is holding the water molecule together, but then you have the hydrogen bond that is holding the molecules together. So that's what holds one water molecule again to another, and each individual water molecule can bond up to 4 other water molecules together. And it's those hydrogen bonds that give water its unique properties, which we'll talk about in the third part of the chapter. You can see it again here. Remember, each water molecule can form 4 hydrogen bonds with up to 4 neighbors. Now, the formation of water from the chemical combination of hydrogen and oxygen is an example of a chemical reaction. And to represent a chemical reaction, scientists will use something called a chemical equation, which we'll see right here. A chemical equation is a shorthand way to notate a chemical reaction. And a chemical reaction is a type of chemical change where the component elements will combine together to create a new type of substance with new properties. Now, regardless of what they form or what they create when the reaction is done, whatever you started with is what you're going to end up with. We call that the law of conservation of matter. So whatever elements come into the reaction are going to be the elements that come out of the reaction in the same proportions. They may seem like they disappeared because they've become a gas or they're in some kind of new combination that's very hard to find, but everything is still there. Matter cannot be created, nor can it be destroyed. There's 2 parts to a reaction. There are the reactants. That's what you start with. These are the reactants. And then what you end up with is called the products. And they're separated by this arrow here. That's called the yield sign. So the reactants will yield or become the products. And in the case of this example reaction here, we have an example reaction that we're looking at in terms of the equation for cellular respiration. So we have a sugar molecule here, which is going to combine with oxygen. That's what we breathe in. And when we exhale, we get carbon dioxide and water, right? Those are the products. But this reaction is not actually correctly notated because it's not balanced, which means it doesn't accurately represent the law of conservation of matter. For example, we have 6 carbons on this side, but we only have 1 carbon on this side. So we have to balance it by using coefficients. And coefficients will indicate the number of molecules present in the reaction. So if I put a 6 here, it will balance my carbons. Now I have 6 on each side. I have 6 hydrogens on the reactant side, but I have 2 here, so I'll put a 6 here, which will make 12. And now I just have to balance out my oxygens by putting a 6 here. 6 times 2 is 12, plus 6 makes 18. I have the same on the other side. This now satisfies the law of conservation of matter, and this is the correct way that the reaction would occur in nature in the appropriate proportions. 1 molecule of glucose plus 6 molecules of oxygen will yield 6 molecules of carbon dioxide and 6 molecules of water. And so we can also represent that graphically with water. This is the chemical reaction for water, and here's the chemical equation showing what happens. It takes 2 molecules of hydrogen plus 1 molecule of oxygen to make 2 molecules of water. And we can see it graphically here because look how many hydrogens we have. 1, 2, 3, 4. On this side I have 1, 2, 3, 4. I have 2 oxygens, 1, 2, 1, 2. So I've satisfied the law of conservation of matter. These are the correct proportions in which the reaction would occur in nature. And so this will be where we'll stop for today. And then the last part of the chapter, we'll talk about water's life-supporting properties and also a little bit about solutions and acids and bases.